Hey, what's up, everybody? Mr. Murray here. I'm Mr. Murray's Mathland, and today we're continuing our polynomial unit here, and specifically taking a function which is a degree greater than a quadratic. If we have one factor, can we use that to find all zeros? And the answer is hopefully, usually, at least at this level. So what we're going to do first is if we have one factor that we know of something, that means we're going to divide it in and find the rest of the factors, right? Just like you would do with numbers. So we are looking for two things here. Part A, we are looking to express this f of x in factored form, right? And so right now I know f of x is equal to x minus 1, that's one of its factors, and then, times what else gives us that 12x cubed, etc. So, I mean, I could sit there and try to guess and check, but I'm going to use synthetic division to help me out with that. And then I'm going to use those factors to find the zeros, of course. And, x minus 1 being a factor means x equals 1 is a solution or a zero of that function. So you already know one of those zeros. And the fundamental theorem of algebra says you should have 3 total zeros because this is x to the third, a third degree or cubic polynomial. So we're going to take that zero we know, which is 1, and we're going to divide it into this. And you could use long division, it should be noted. But if your divisor is 1x to the first, you can use synthetic division, and that's what I'm going to do because it's fast. So hopefully if you're watching this video, you have some familiarity with synthetic division. So I take a quick look at this polynomial. 12x cubed minus 11x squared minus 7x plus 6. No need for any zero placeholders because we've got one term for everything from that third degree down. So I can just take those coefficients, 12, negative 11, minus 7, and positive 6 for the constant, right? We start by bringing down that leading coefficient of 12, and then 12 times the 1 that's out there in the box gives us positive 12. Combine that, put that underneath the next column. Negative 11 plus 12 gives us positive 1. Positive 1 times 1 is 1. Negative 7 plus 1 is negative 6. And negative 6 times that 1 in the box is negative 6, leaving us our remainder. And since we know that this is a factor, we should be getting a remainder of 0. So that's kind of a nice check to make sure you didn't make a silly addition or multiplication mistake along the way. Okay, so now what have we figured out? Well, we take this quotient that came out, 12x squared, right? 1 degree lower than we divide it into, right? Because every time you divide it, it reduces it by 1 degree. And this is plus 1x minus 6. This is the quadratic that if you multiply times x minus 1, you would get that f of x cubic. So now we are looking to factor that, if possible. Does this quadratic factor down further? And if so, you could sit there and there's a lot of ways to do this. The AC method, the kind of guess and check with combinations, 12x squared, is it 12x and 1x? Is it 4x and 3x or 6x and 2x? You got to go through those combinations. The more there are, the more annoying it can be. Negative 6 here, that could be 6 and 1, 3 and 2, positive, negative. And, if you're pretty good with that, it can be pretty fast. I'm going to do a little variation on the AC method, which, I sometimes do if there's a lot of combinations, is I take the A value of 12 times the C value of negative 6, and I get negative 72. And then, does anything multiply to negative 72 and add up to positive 1? That's that middle term. And that's 9 and negative 8. And that at least tells you that it does, in fact, factor, regardless of how you want to proceed from here. So just know that it does have to factor. So now how you do it, here's a little trick with these to finish it off fast. If you have those two magic numbers, 9 and negative 8, is I take 12x squared and I break it up into two fractions. And I put 12x on top of each one, 12x over 9, 12x over negative 8. because I'm not sure how that 12 is going to break it up, right? 12x and 1x or 6x and 2x, but you put it over these and you reduce the fractions. Let's see, 12 over 9 reduces to 4 over 3. 12 over negative 8 reduces to 3 over negative 2. And then those are your binomials. 4x positive 3. 4x plus 3. 3x minus 2. Right? Okay, so there we go. And then our two other zeros come from those. When you set these each equal to 0, you're going to get x equals negative 3/4 and x equals positive 2/3. So there we go. Now that's a good solid example there. But I must admit this video is a little bit longer than usual because I had 3 really good examples. Each one has a little bit of a different twist, either with factoring or solving or whatever. But so I couldn't help it. So this one's gonna be a little bit longer, but still it's just chock full of good stuff. You know, don't skip out on it. If you want to even fast forward to see the other examples, there's 3 total examples. All right, so here's number 2. Express this in factored form. Now this is an x to the 5th, right? So this should have 5 zeros. And we know that x plus 3 is one factor of this. So we got some work to do with this. And for part B, for our zeros, of course, that x plus 3 is going to yield x equals negative 3. And that's all we got right now. So negative 3 goes in the little synthetic box, or however you like to set it up. Some people do that with a big L. No 0 placeholders necessary. I'm looking. So here we go. We're going to write into these coefficients. 1 from the x to the 5th, positive 3 from the x to the 4th, minus 8x cubed, minus 24x squared, minus 48x, minus 144. Run out of room a little bit there. Just be a little careful. Okay, so bring down that 1 and we're off and running. You know, if you do synthetic division, you know you can kind of fly with these. 1 times negative 3 is negative 3. Those add to give you 0, which is kind of cool. 0 times negative 3 is 0. You get negative 8, negative 3, positive 24. You get another 0 there. Multiply 0 times negative 3, you get 0. Combine that, negative 48. Negative 48 times negative 3. And again, if you're feeling like this isn't a weird one, just double check, make sure you get a remainder of 0. And 48 times 3 is 144. So we do, in fact, have a remainder of 0. Yes, I like to put a little smiley face. It makes me happy. So what do we have left from this? We have 1x to the 4th, 1 degree lower. This 0 would represent x cubed, but we don't have any of those. So this is minus 8x squared. This 0 would be x to the 1st. We don't have any of those. And that's minus 48 as a constant. So here's what we have so far. We have x plus 3, and we know we have this quartic function. X to the 4th minus 8x squared minus 48. Now, does that factor any further here? Well, the good thing is this is what we call quadratic form because it's a trinomial, and x squared would give you x to the 4th. So it follows the same basic pattern as any other quadratic, except when it factors, it's going to be x squared and x squared. And now what multiplies to negative 48 and adds up to negative 8? You know, the leading coefficient of this was 1, so no need for any AC or fraction tricks here. So that would be a negative 12 and positive 4, right? It multiplies to negative 48, but adds up to that negative 8 in the middle. And neither of those factors any further, right? X squared minus 12, but 12 is not a perfect square. And x squared plus 4, 4 is a perfect square, but it's a sum, and there's no sum of 2 squares. So this is completely factored, but now let's get the zeros from it. So I'm just going to shift this down a little bit, give myself a little more room to work with. Try not to be too impressed with the technical skills there. But when I set these equal to 0, when you set x squared minus 12 equals 0, you get x squared equals 12. And to solve this, we're going to take the square root of both sides, and just remember your basic algebra, very common mistake. When you take the square root of both sides of an equation to solve, you need to consider positive and negative square root of that side, right? Because it's x squared. There should be 2 solutions to that. So plus or minus root 12, and of course that would break down to plus or minus 2 root 3, right? Root 4 times root 3, and the square root of 4 is 2. Okay, so there's 2 more zeros. We have 3 total, and this final x squared plus 4 is going to yield the final 2 zeros. And when you set that equal to 0, x squared equals negative 4. So we get a similar thing here. X equals plus or minus the square root of that negative 4. And hopefully that's catching your eye, you know, if you're a little rusty with these things, that taking the square root of a negative is imaginary. So the way you handle this, remember, is separate the negative. So you factor out negative 1, and the square root of negative 1 is that component I for imaginary. And 4 is actually a perfect square, so we actually get plus or minus 2 I. And there we go. There's all 5 zeros from that. So that's why that was a good example there, because it had some factoring of an x to the 4th that's in quadratic form, and gave us a little plus or minus and a little imaginary action. So lots of good little algebra nuggets in that one problem. And finally, here's number 3, and I promise you this has some good one too, some good quirks in it. So yeah, I'm really nerding out over these problems. It's just such classic algebra, and so many things go into each problem. So we have x minus 2 here as our known factor of this x to the 5th. So of course, we've got the x minus 2 for our factored form, and for our zeros, we've got 1 to get started. And that, of course, is x equals 2 when we set that known factor equal to 0. And 2 is what we put in the little synthetic box out here. Any 0 placeholders necessary? No, I don't believe so. So there we go. 16x to the 5th minus 40x to the 4th plus 16x cubed plus 54x squared minus 135x to the 1st plus 54 on the end. Bring down that leading coefficient as the first part of your quotient, and then 16 times 2 is positive 32, negative 42 and 32 is negative 8, negative 8 times 2 is negative 16. There's a 0, 0 times 2 is 0, 54 and 0 is 54, 54 times 2 is positive 108, negative 135 and positive 108 is negative 27, and negative 27 times positive 2 is negative 54, giving us that expected remainder of 0. Gives us a little confidence boost, no careless mistakes. And then our quotient here, what came out of that is 16x to the 4th minus 8x cubed, 0x squared plus 54x to the 1st minus 27. So this right here is what we're now trying to factor and solve. And this has 4 terms in it, so I'm going to use a little technique called grouping, right? It's been a while, and our first grouping strategy is typically try to group them 2 and 2. That's the most common way. And of course, out of the first 2, you can take out a greatest common factor of 8x cubed. When I take 8x cubed out, that'll be 2x minus 1. Out of the second group, it starts with a positive, so I'm going to take out a positive, and you can take out 27 out of that, and that will be 2x minus 1, and that's how you know that you're almost, done, at least with the grouping part, that it has worked, is when you have that common factor that appears twice. So then you basically factor out that common factor of 2x minus 1, and your other polynomial factor is made up of those coefficients of 8x cubed and positive 27. Okay, so now that's what this has factored into, and that's what would be right here. But does this factor any further? And hopefully you're looking at that and saying, yes, that's a sum of 2 perfect cubes. So we get to review a little factoring sum of cubes here. See, I told you this had some good stuff in it. So factoring a sum of cubes, let's quick little review here, right? Sum of cubes and difference of cubes have the same, kind of pattern here. A cubed plus or minus b cubed. right? They both factor this way to a binomial times a trinomial, a squared, b squared. They both have that same pattern. The only difference is their signs, and I cleverly tell my class to think of the word SOAP. SOAP being that the first sign is always the same as whatever you're factoring. So if you're factoring a sum, it's a plus. If you're factoring a difference of cubes, it's a minus. Same, and then the second sign is opposite, so that would be a minus if you're factoring a difference, a plus if you're factoring a difference, and the last sign is always positive. So same, opposite, always positive. And A and B are, of course, what cubes to give you these two terms, or in fact the cube roots of them. So the cube root of 8x cubed is 2x. The cube root of 27 is 3. So that's your A, that's your B. So A squared would be 4x squared. Don't forget to square the 2 as well as the x. B squared on the end there would be 9 when you square 3. And in the middle is AB, not 2AB, as sometimes kids get a little confused. So AB, 2x times 3 is 6x. And the signs are same. It's a sum, so that's plus. Opposite, so minus. Always positive. And that is completely factored now. You might look at that and think that you can factor further. Yeah, I'm getting lazy here. It didn't work out so well. I'll edit it out. Who am I kidding? I'm not going to edit it out either. You're going to watch it and enjoy it. You might think that second quadratic there at the end factors further, but it doesn't. It never factors any further if you've done it correctly. Just give myself a little space here. 4x squared minus 6x plus 9, and you might take a look at it if it looks like it might, but 4 times 9 is positive 36. Nothing will multiply to positive 36 and add up to negative 6. And that it never happens with the sum and difference of cubes. So, if you know you've done it right, don't even bother trying to factor further. Okay, so now to get the zeros, that should be pretty easy, right? We take each factor. We've already taken the first factor. The factor of 2x minus 1 should give us x equals positive 1/2. The factor of 2x plus 3 should give us x equals negative 3/2. And, I'm just going to give myself a little more room. But now this last quadratic that contains the final two zeros of this, giving us a total of 5, if that doesn't factor, how do we solve it? Well, that's where you got your quadratic formula. Or you could do completing the square if any of you are fans of that, but the quadratic formula is often faster than that. So here we go. So like I said, this is got a lot of stuff in it, old classics here. A, B, and C. So our quadratic formula, x equals negative b plus or minus the square root of b squared. So negative 6 squared is 36. I'm going to do some of this as I go. Minus 4 times a times c, 4 times 9 is 36. For whatever reason, I always do the AC part and then multiply by 4 all over 2a, so all over 2 times 4. So now let's get simplifying this. This is 6 plus or minus the square root of. Now on the inside there, that's 36 minus 4 times 36 is 144, and 36 minus 144 is negative 108. And it's all divided by 2 times 4, which is 8. So we've got a square root of a negative number, so we've got more imaginary, or in this case complex, zeros. 6 plus or minus, what does root negative 108 reduce to? Well, you're definitely going to take out the negative, and that's the I. And root 108, not a perfect square, but you can take out 36, right? So that'll be root 36, and root 3 left over, so that'll be 6I root 3, all divided by 8. And finally, when you take a look at this, If you're dividing all of this by 8, you can divide each term by 2 to reduce that fraction. So 3 plus or minus 3I root 3 when you divide those 6's by 2 and divide that 8 by 2, and you have 4. And those are your last two zeros there. 3 plus or minus 3I root 3 over 4. Or if you have a teacher who's asked you to put it in standard form, they might be a bit of a stickler on this, so just remember, to standard form means to separate the real and imaginary components. So that would really be breaking that up into 3/4 plus 3 root 3 over 4I and 3 over 4 minus 3 root 3 over 4I. Yes, really breaking those up and putting the I after, treating this as the b value, as the big coefficient of I. That's technically standard form, but there's the zeros. Very nice, right? Great problem, lots of good stuff in there, lots of factoring, lots of algebra. So hopefully you're enjoying this stuff and hanging in there. But if you got any questions, let me know. Otherwise, keep working hard and keep mathing on, kids.